Now, I just wanted to spend a couple of slides talking about eigenvalue equations. The reason being is that a lot of students and myself, when I was first doing quantum mechanics, for me, eigenvalues and eigenvectors were something that fell out of the sky like magic, especially for quantum mechanics. But that is not the case. They are a normal part of mathematics. So I'd like to just spend a little bit of time on them. So if we write out an eigenvalue equation, we have t, a function, an operator, something that operates on a, which is a vector. It gives us a number lambda times the same vector. Okay, so this is the same vector, and lambda is a number. Now, if we try to think about that in three-dimensional space, when you're talking about vectors, even if they can be n-dimensional or infinite dimensional, it's always good to go back to three-dimensional real space, where we're very good at working there because we've been working there for years. If you have a vector pointing in a particular direction and you operate on it, as you can see from the eigenvalue equation, you end up with the same vector just multiplied by a number. So you end up with the same vector, let's say multiplied by 2, or multiplied by a half, or pointing in the opposite direction, but still lying along the same line of that vector. And so one can think of what could be, just in three-dimensional real space, the operations that t could do. If the vector starts from the origin, it could rotate it by 180 degrees. Now it's pointing in the opposite direction. It's the same effect as multiplying by -1. Or you could rotate it around the axis along which it lies. If you have a vector, you hold out a stick and you rotate it along the direction it's pointing, nothing happens, nothing changes. So it is still a vector. Okay, in that case, lambda would be 1. You could also rotate in a different direction around the origin, but just to point back. Or you could rotate 360 degrees around the origin and point along the same line. So that's what an eigenvalue equation means. It seems a bit strange, but when you move to n dimensions, it becomes more useful. Now, a is a vector, okay? T is some function, okay? And now usually we write vectors as column vectors. If you looked at the video by Sabine Hossenfelder, she mentions it. But here we have the vector a, a1, a2, a3, 4, all the way to an, are just the coefficients of the basis we're working in. And if that confuses you slightly, as always, go back to 3 dimensions. So in 3 dimensions, pick a vector, a equals 3x plus 4y plus 5z. Our basis is x, y, z, because it's the easiest and simplest to work with. And you would write that as 3, 4, 5, okay, where the basis is implied. Now, if A is a n by 1 column matrix, and you need to act on it with something that will give you another n by 1 column matrix, that means that T has to be an n by n matrix, because if you act with an n by n matrix on an n by 1 vector, you will end up with an n by 1 vector. If you remember your matrix multiplication. So T is an n by n matrix. Okay, now if we look at this eigenvalue equation and we assume that a is not equal to 0, a can be equal to 0. It is a valid eigenvalue, but it's kind of a trivial, boring one, so we're going to say a is not equal to 0. So if I bring everything over to the left-hand side, then I have t minus lambda I acting on a is equal to 0. I is just the identity matrix, because you can't go matrix minus a number. You have to go matrix minus a number multiplied by the identity matrix, where the identity matrix is just a line of ones that lie along the diagonal. Now, if t minus lambda I had an inverse, if 1 over t minus lambda I existed, then we could multiply both sides by 1 over t minus lambda I, and then we would get that a is equal to 0, okay, which is not the case, okay, which means that t minus lambda I does not have an inverse, okay, and a matrix with no inverse is called singular. You don't have to remember that term, but the important thing is that if a matrix does not have an inverse, it means that its determinant is 0. Okay, so the determinant of t minus lambda I, which I've written out there in full, is equal to 0. And that's how you would have solved eigenvalue equations for the eigenvalues. You would have written out this, this matrix, and you would have put the minus lambdas all the way along the diagonal. And this is just showing you where that comes from. Okay, it's really a 3-line proof, but it maybe makes you understand better why, when one solves for eigenvalues, one does that. And why are eigenvalues important? Well, in quantum mechanics, they would be written a bit more like this. The hat is often used to denote an operator. In this case, we use psi, because psi is what we usually use for a wave function. The hat doesn't always have to be there. It's usually there when there could be confusion about whether it's an operator or not. If it's clear that it's an operator, one can leave the hat out. But more importantly, this equation, which you definitely should know, the time-independent Schrödinger equation, the Hamiltonian times the wave function is equal to the energy times the wave function, is one of the most important equations in quantum mechanics, and that is very clearly an eigenvalue equation. And that is why eigenvalue equations are so important.